Hello, welcome to the Kavli Foundation's live interview with astrophysicist Louis Strigari of the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University in California. My name is Bruce Lieberman. Today's we'll be talking about nomad planets, which researchers discovered only about a year ago. Unlike planets in our own solar system, nomad planets are unbound to any star. They experience no daylight, no sunrise or sunset, no change of seasons. They're essentially drifting through space in eternal night. Dr. Strigari, who studies the properties of dark matter, the formation of galaxies, and the structure of our own Milky Way Galaxy, the Milky Way, has estimated with his colleagues that nomad planets are incredibly numerous. They might number in the quadrillions, just here in our own galaxy. Recently, I interviewed Dr. Strigari, along with scientists Roger Blandford, director of the Kavli Institute at Stanford, and Dimitar Sasolov of Harvard University, about nomad planets. You can find that conversation at the Kavli Foundation website. But today, we're opening up questions to a larger audience. I'll be asking questions that have been emailed over the past week, as well as questions that come in over the next 30 minutes. To begin, Dr. Strigari, I'd like to ask you, how do we even know that nomad planets exist, and how have we found them?
That's a good question. Well, the story actually starts with Einstein, who predicted that space around massive objects get deformed. And if you imagine a light ray following around this massive body, the light ray traces out the deformation in space. So if you imagine a situation in which we, an observer here on Earth, are looking at a background star, and there's a massive body that passes in between us and the background star, the light from that massive star will temporarily get deformed as the body passes in front of the star. And as such, the body will act as a gravitational lens that changes the light distribution coming from the background star. So via this method, one can deduce, even if you can't measure or see the massive body passing in between us and the star, you can deduce that it's there just because it changes the amount of light that we see from the background star.
So the star momentarily brightens, is that right?
The star momentarily brightens, that is in fact correct. And this effect was predicted by Einstein going back to the 1930s. However, given what he knew at the time about the distribution of stars and the number of stars in the Milky Way Galaxy, he famously predicted that this effect would never be able to be observed. However, in the intervening years, within the past century, we've learned more about how many stars there are in the galaxy, and this effect, which is particularly called gravitational microlensing, is now observed as a common phenomena in the realm of astronomy.
One question that came in over the past week asks, how do we know that when we see this momentary brightening of a star, how do we know that it's a nomad planet or perhaps, say, a brown dwarf, which is a kind of failed star?
That's a good question. Well, we don't know exactly what it is or where it is. All we can say is that the body is somewhere between us and the background star. We don't really know exactly how fast it's moving, how massive it is, or how distant it is, but we know some combination of these parameters. And very generally, what we'd expect from a lighter mass body, say a nomad planet that might weigh as much as a Jupiter-type body or a brown dwarf, we know that it will distort the light from the background star over a smaller time period than, say, an object as massive as the sun or much more massive than the sun would. So basically, by looking at how fast the light curve changes from the background star, one can deduce very roughly how massive the body is.
So if it's a very massive object like a brown dwarf or something that is not a nomad planet, you're going to see a much more intense momentary brightening of that star. Is that right?
Yeah, so what happens if you have a very massive object that maybe weighs 10 times the mass of the sun, the brightening might last the scales of months to even years. But if it's a nomad planet that weighs as much as Jupiter or even a brown dwarf, you could only see characteristic changes in the light from the star over the scales of hours to days even. That's right.
I wanted to ask you something about your paper, and a question came in inquiring about this. How did you estimate how many nomad planets you expect to be out in the Milky Way? How did you arrive at that number?
Oh yeah, so since the discoveries were made, initial discoveries were made about a year ago, it sort of brought to light this idea that we really have no idea in order of magnitude how many of these objects actually exist in our galaxy. So really the simple question we tried to address is how many could possibly exist given the bounds that we know from astrophysics and cosmology. So basically what we did is we took up all of the matter that we knew in the galaxy that is heavier than helium, so-called what astronomers might call metals. Okay, so you might think of oxygen, nitrogen, these types of elements in this context, and counted how much of that exists in our galaxy. And then along with understanding how much gravitational pull is exerted on stars in our galaxy, one can deduce an upper bound of how many of these objects actually exist per star in our galaxy. So then that's how we came up with this number of approximately 10 to the 5 nomad planets per star in our galaxy. Now, even though this seems like a very, very large number, what one has to realize is there's likely much more mass in these objects, or there's likely many more of these objects at very low masses than there are at very high masses. So there's likely not hundreds of Jupiter mass bodies per star, but there could easily be, 10 to the 5 objects as massive as Pluto per star floating in our galaxy. And we don't really have any good gauge of how the inventory of massive objects at this scale, at this stage.
Now, in our earlier talk, I asked you about how many of these nomad planets we might expect to see between us and the nearest star to our own solar system, because quadrillion sounds like a lot of objects. So, if we are traveling from here to Proxima Centauri, how many are we going to run into?
That's a good question, and we still don't know that number to within orders of magnitude yet. Sort of going from this upper limit that we deduced, it's not implausible that several of these objects about as massive as Pluto, or maybe a little more massive or less massive, might exist in between us and the nearest star. So to sort of put this, to sort of give a gauge to how little we know, just really within the past decades, we're now starting to discover small bodies as massive as Pluto out in the outer regions of our solar system that orbit the sun at radii hundreds to thousands of AU. So really, we're just getting inventory of these types of objects, even in the outer reaches of our own solar system. So it's really not implausible to conjecture that these things exist sort of floating out in the regions between us and the nearest star as well.
So you've studied very early forming solar systems where stars form and they have this disk of gas and dust surrounding the star, and that disk, through self-gravitation, forms into planets and asteroids and other things. And you've speculated that these objects might be exchanged, early planets could be exchanged between solar systems. Tell us a little bit about that idea.
Yeah, that's correct. Actually, most stars, like the sun, are believed to form in clusters in which the stars are more densely packed than they are as we see them today. And during this process of the formation of the sun and other stars, as you mentioned, sort of these protoplanetary disks form around every star. And being the spacing in between the stars is much less than it is as we see it today, it's very plausible that these protoplanetary disks have interacted with one another. So bodies that can form around a particular star get influenced by the bodies and the gravity of another star in the cluster. And there have been, in the past several years, numerical simulations and calculations that have been done that show that it's in fact very common for stars in this manner to exchange planets or planetary mass bodies in between them, such that upwards of 50%, if not more, of the comets that one might see around that are bound to a given star might have originated from another star and been born around another star in the cluster. So this idea of exchanging, of not only ejecting nomad planets out into interstellar space, but also exchanging these objects between stars, now we're starting to theoretically realize that this actually might be a very common process in the formation of our galaxy and in various stars in our galaxy.
So our own sun, the nearest star to our own sun, is about 4 light years away, or about 24 trillion miles. Is that right? Or
more or less.
I might have the miles wrong, but we're talking about early forming solar systems that are much closer to.
That's right. Yeah. So the sun and other stars like the sun are believed to form in clusters of stars, and then this cluster disperses on the scales of 1 to 10-ish mega years. such that the spacing between the stars is much larger than we see. The spacing between the stars right now is much larger than it was in the past. So even today, you actually might even deduce that maybe nearby stars could pass within the realm of the sun and sort of and change the orbits of outer bodies in the outer Oort cloud. Earlier on in the formation of the sun, in the formation of planetary systems and stars like the sun, this process was believed to be much more common than it might be today.
So this next question from the audience has something that I've been interested in, and that is you've used this gravitational microlensing technique to discover nomad planets and to study them. But what other methods of detection are available with today's technology? And I want to add on to that question I have as well, and that's will this technology either today or in the future actually be able to help us understand where these objects are between the star that it's brightening and the Earth?
That's a really good question. Actually, so the gravitational lensing technique, what is really interesting about it and is really great about it is it can detect nomad planets really pretty much anywhere in our galaxy. Unfortunately, for objects that are very far away from us towards the center of a galaxy, there's really probably no feasible way at this stage to directly see them or directly see reflected light from these bodies. However, it's not impossible that that for bodies maybe within, say, thousands of AU from us, it's not implausible that we could see direct light that's emitted from the body, or even reflected light from the sun that comes from that body. So really, we're left with a situation that the microlensing, the gravitational lensing technique can detect these bodies anywhere in the galaxy. But if one happens to be very nearby, then it's not implausible we could see the direct light, such as we see objects sort of beyond the orbit of Pluto, such as Sedna, and these small bodies of the outer solar system. So it's not implausible that something like that could occur if we have a good idea about where to look to find one of these bodies.
And we could potentially detect their infrared radiation, the heat that they give off?
Yeah, that's right. It'd be a very, very faint amount of infrared radiation. Now, also to note, there's in the next decade or so, there'll be surveys that are coming online that will be able to perhaps detect these objects. That these will be sort of almost full sky surveys that will be sensitive to potentially seeing these objects, because they'll continually take pictures of the sky every day or so. So in this sense, if the object is very nearby, also you could see it move across the sky relative to background stars. So this might be another way to help directly detecting these objects.
And what is that future instrument that you
this would be, I'm speaking particularly of an object like the Large Synoptic Survey Telescope. Currently, we have the Pan-STARRS telescope is currently working to search for small bodies in our solar system and look for these types of objects as well. But on a larger scale, we'd be talking about the Large Synoptic Survey Telescope, which hopefully will start operating in about a decade or so, that could detect many of these faint bodies in the outer reaches of our solar system and beyond.
So Pan-STARRS, where is that?
Oh, that's in Hawaii right now.
In Hawaii. And then the LSST is a space-based mission?
Yeah, well, the LSST is a ground-based mission, but the interesting thing about LSST, it'll have a very, very, very small cadence, such that it'll take pictures of the sky of order every day or so. So really, it'll be able to, if an object is moving and we can see the faint light from an object just by looking at different frames, we can actually see the body move across the sky with an instrument like this, which would be really fantastic.
Okay, great. Well, when we wrap up, I want to ask you about future directions for research and some of the big questions that you have. But we have some other questions from the audience here, and here's an interesting one. It says that since some of the nomad planets may have formed in dust clouds along with stars, which we talked about, right, they could be fairly old. So do you have any estimates on what the oldest nomad planets might be?
They could be as old as our solar system, 4.5 billion years old, if not much older. It's very plausible even before our sun formed, there was a generation of stars that formed in our galaxy that made planets and ejected planets from their own stellar systems. And it's very plausible that these objects might still be captured in the gravitational influence of the Milky Way Galaxy, and these objects maybe still be roaming around our Milky Way Galaxy itself. So really, there's no limit to how old these things can be. Really, just they might come from first generations of stars that have formed. Also, it's very plausible that our Milky Way Galaxy has merged with other small galaxies in the past. So it's not implausible that other galaxies have brought in a population of nomad planets with them into our Milky Way Galaxy. So really, we're in a situation where we're just starting to scratch the surface as far as understanding theoretically where can these possibly come from.
So you're saying that nomad planets could theoretically be exchanged between galaxies when galaxies merge?
Exactly. Yeah. So we have a pretty good idea that our own Milky Way Galaxy was built up from the formation of smaller galaxies during the evolution of the universe. So really, plausible at all to speculate that these galaxies that emerged have brought in populations of nomad planets with them. So really, it's an interesting question now to ask: what is more probable? Where is more probable for a given nomad planet to come? Will it more likely come from an external galaxy, or could it come sort of internally produced from our own galaxy and have been ejected from a stellar system in our own galaxy? I think, as I mentioned, these are really interesting questions that we're not just now starting to be able to come to grips with and address theoretically.
So these nomad planets, I mean, they're true wanderers. I mean, they not only are not orbiting a particular star within our galaxy, but they could be, during the merger of two galaxies, be flung out into intergalactic space. They're going to be pretty lonely then.
That is true. They could be true nomad planets, the nomads going through not only interstellar space but intergalactic space. And it's definitely true that we see debris from merging galaxies, not only in our own galaxy but also in external galaxies. And it's very plausible that during this process, planetary mass bodies, nomads, have been ejected and dispersed via this merging process through intergalactic space.
So we have some questions that just came in. I'd like to ask you. This is a good one, and we're going to switch gears a little bit. Do you believe nomad planets could be carriers of life in the universe? So I'd like to back up a little bit and focus on the speculation that you offered in your recent paper a little bit about how life might be able to be sustained on these planets that get no warmth from any sun and have no, as I said, no seasons, no sunrise, no sunset. How could life possibly exist on these objects?
Well, I think at this point it's interesting to sort of just take a step back and say, really, what we're coming to learn about life on Earth is that it's possible to exist in what we might, on the surface, think of as really inhospitable environments. And we know of microbes that are able to survive just in the deep in ocean vents, just on heat that comes from the Earth. So
with no exposure to sunlight at all.
No exposure to sunlight, no. So in that sense, it's not implausible that if, let's say, you imagine a scenario in which a nomad planet gets ejected from a given stellar system and is wandering out in interstellar space, and let's say this nomad planet has a sort of a high pressurized hydrogen atmosphere that's thick enough to trap infrared radiation on the surface. You can certainly imagine that life having formed in this type of inhospitable environment might not, and in fact will not, cease to exist, even though the body does not orbit around any star. So really, it's not implausible at all to think that these objects could be carriers of life in the universe and in the galaxy, and a possible means to spread at least microbial life through our galaxy. And once again, I think these are interesting questions that we're just starting to address from both the perspective of astronomy and also from the perspective of biology.
So to generate or sustain life, a planet needs a source of heat, and planets in their core have this radioactive elements that will generate heat over very long periods of time. And so you have heat coming up from the interior of a planet, and if it has one of these atmospheres, that will, like a blanket, lock in that heat. Is that right?
Exactly. So that heat will come from the radioactive processes, as you mentioned, which we know happen on the Earth. Also, there just could be latent heat that comes out from the formation of the core of the planetary mass body. So there's various heating mechanisms. Also, you can imagine that if the Nomad has a system of moons floating around it, there could be tectonic activity on the surface from the system of moons that generates heat. In fact, some calculations have recently shown that it's not implausible to eject not only a Nomad planet from the galaxy, but also its system of moons might be carried along with it. So really, in that sense, it would be a true Nomad object, sort of tending to its own flock in that regards.
And those moons, as they orbit the Nomad planet, could generate some tidal friction on the surface of that planet.
Exactly, and that would also be a heat mechanism, and this would also be trapped if the object had a sort of a high pressurized atmosphere that was capable of retaining this heat and capable of sustaining life that might exist on it.
Okay, we have another question that came in, which asks about planets in general. So we've been talking about Nomad planets being some of them being very large, probably many more of them being very small on the order of perhaps Pluto, the size of Pluto. So how big or small can a planet become just in general? How large or small can it be?
That's a good question. We don't really know the answer. So for generations, we had one solar system to look at for a prototype of what a planet could be and what a planet could not be. So we had this idea that the most massive planets, or the gas giant planets, where likely you might have a situation where there's a rocky core in the center of these objects, and that hydrogen helium gas have been accreted to make a gas giant body, such as we see in Jupiter and the Saturn type of object. And then on the other hand, you have rocky bodies such as the Earth, primarily rocky bodies such as the Earth, Venus, Mars, and Mercury. With in some instances, you may have an atmosphere around the object. So now what we're finding from the discovery of planets orbiting other stars is that actually our solar system is not the norm, and in fact it might be an outlier in how regular it appears to be. In discoveries of exoplanets around other stars, now we see Jupiter mass bodies or even larger orbiting very, very close into their stars. We see likely rocky bodies is like the Earth, about 10 times more massive than the Earth, that are orbiting very close to their stars as well. So I think really right now we have no good theoretical guidance for what a given planet can consist of, how massive it can possibly be. I think right now we're sort of being guided by these brand new observations and trying to put together the theoretical picture from these observations. So really, I think we just have to we have to keep an open mind about what is possible out there at this stage.
So our own solar system is hardly an archetype. The idea that small rocky planets are closer to the sun, large gaseous planets toward the outside. And now Nomad planets add a completely new wrinkle to them.
That's correct. Yeah, as I mentioned, we now see Jupiter mass bodies, if not larger, orbiting their parent stars at about, say, the radius of where Mercury is relative to our own sun. We see so-called super Earths that are orbiting very close into their parent stars. And these objects would be about 10 times as massive as the Earth. We don't know exactly yet what they're made of, but we can deduce roughly how big they are just by the observations of them. And also regarding the Nomad planets, it's really long been speculated that it's fairly straightforward to eject planetary mass bodies from protostellar systems. What's really puzzling about the current observations is there appears to be many more bodies out there that have been ejected as nomads than we could have possibly accounted for from sort of basic theoretical investigation. So I think this combination of understanding the population of nomads as well as understanding how planetary systems form around given stars really is a great theoretical challenge for us going forward.
So we've talked about how nomad planets might have the conditions that could promote life or sustain life. But one of the questions here was how would a planet that is formed without a star be different from one that was formed with a star? And I think this suggests what we've talked about before, and that is nomad planets can be can happen when they are ejected from an early forming solar system. But nomad planets can also be formed in the same way, general way that stars are formed in these huge clouds of gas and dust, forming independently of a star in the first place. Is that right?
That's correct.
And how would that kind of planet be different than one that's formed with a star?
it's not certain. What we do know is there's probably a lower bound of the mass of an object that can form from the collapse of a molecular cloud of gas in the way that a star forms, and that mass in our own galaxy happens to be somewhere around the mass of Jupiter or so. So if we see sort of freely floating body as massive as Jupiter or larger, it could really have two origins. It could have been born around a planetary system and been ejected, or it could have sort of formed just in its own right in the ways that stars and low mass stars and brown dwarfs form. But at lower masses, say going down to Saturn mass, Earth mass, et cetera, and below, according to our theoretical understanding right now, we believe these objects, as you mentioned, formed around protoplanetary disks and then got ejected from the disks out into interstellar space. And sort of that's probably the most plausible scenario we have at this time. Also, I mentioned too, we have this scenario where nomad planets could be merging from other galaxies. So really, there's lots of different sources of these objects at this stage, and I think that's one thing that's really exciting going forward, to try to understand what are the possible limitations and in realistic scenarios about where these can come from.
Just wanted to clarify some terminology. You've been referring to, I believe, nomad planets as planetary objects, or quote unquote objects. Are you using those terms interchangeably? That we're focused on nomad planets. Is that right?
Yeah. So when I say, I guess the standard astronomical definition for a planet now is a body that's massive enough to sweep out its own orbit around a given star. So this sort of lends itself to a very specific definition, which is why we wanted to introduce this concept of a nomad. A lot of times people call these freely floating planets or rogue planets, but we really thought that definition wasn't appropriate in this context, because a planet, and now to us in astronomy, needs something much more specific. And this has in particular come to light now with the discoveries of bodies as massive as Pluto out in the outer solar system. Sort of it made us rethink of what our definition of, in fact, what a planet is.
Okay. So we've talked about the idea of nomad planets possibly harboring life or sustaining life after they're ejected from solar systems because of various conditions that it might have. But there's a lot of talk. One of your areas of study is dark matter, and dark matter, as many astronomers know it or talk about it, is this mysterious substance that we really have no idea what it is, but it accounts for a lot of the gravitational effects we see on cosmological scales, on galactic scales, and in galaxy clusters and so on. But within our Milky Way, there are a lot of dark, quote unquote, dark objects as well, and then these nomad planets are kind of in that category. To what extent could nomad planets actually be part of that dark matter that would explain the gravitational effects that we see?
Well, you have to. So one of the inputs in our calculation was that we have a pretty good idea of the matter budget in the universe. There's about 5 times more dark matter than there is ordinary matter, i.e., the kind of matter that you and I are most used to. So there's about.
And you know that based on what?
We know that from a variety of measurements, from large-scale measurements in cosmology, from measurements of rotation curves of galaxies, from measurements of the cosmic microwave background. Sort of this general consensus, the standard cosmological model has come together to tell us that most of the matter that we see around galaxies is dark and is likely in the form of some new elementary particle of nature that we have yet to detect or yet to create in the lab.
So where do nomad planets fit in that picture?
So nomad planets would be more. They would have. They formed from the ordinary matter that you and I know of. Okay, so that's what they're contained of. They might be contained of. Like I mentioned before, oxygen, nitrogen, these types of elements that we know of on the periodic table, and sort of. And a bound that went into our calculation was we know how many of those objects, how much of that mass, how much mass there is in ordinary matter in our galaxy and in the universe. Okay, and there can't be many more. Or there can't be any more nomad planets than there is mass and ordinary matter that we know of in our galaxy.
All right, we're coming up to the end soon, so I just wanted to ask you quickly, what are your biggest questions you have about nomad planets, and just real quickly, and then we'll wrap up.
So yeah, I actually am really interested in where they came from, what fraction can come from our own galaxy, what fraction can come from other galaxies. Can we, as we talked about earlier, how easy is it for even planetary mass bodies to get exchanged from one planet to another? How likely it is for a given object to become a nomad planet? And of course, there's the question of life, and is this a realistic means to spread life through our galaxy and through the universe at large?
Terrific. Well, thank you, Dr. Strigari, for joining us today, and thanks to everyone for watching today. A video podcast will be posted to the Kavli Foundation website at kavlifoundation.org, and have a great day.